Hi, everyone. I'm Qian, a fifth-year PhD student at Columbia Business School. Today, I'm very excited to talk about a recent work joined with Yash Kanoria. In this work, we talk about the online control in closed queuing networks. This model has applications in shared transportation systems and script systems, etc. Now let me use a cartoon to illustrate the key elements of our model and the key trade-off we're considering. Let's consider a node network. For example, in ride-hailing, you can think of the nodes as physical locations. And there are a fixed number of supply units that circulate within the network, represented by the cars here. So the supply units, they don't enter or exit the system. That's why we call the system closed. Demands arrive to the system over time in a stochastic fashion. For example, this guy wants to go from location 1 to location 3. And the platform needs to make decisions, such as entry control decisions. For example, if the platform decides to serve this guy, the upside is the platform can collect a payoff of W, but the downside is a car will be relocated to the location 3. And location 1 now doesn't have cars anymore. This may impact the platform's capacity of serving customers in the future. So the key trade-off here is how to manage the supply distribution within the network while maximizing objectives such as payoff. This model has many applications. For example, we just talked about ride-hailing. In ride-hailing, there are many control levels of interest. I just introduced entry control. You can also consider pricing control, where the price can be used to regulate the demand arrival rates. You can also consider assignment control. For example, when a demand arrives, the system can decide from which neighboring location to dispatch a car to pick up the customer. People have also started repositioning of empty cars, etc. Another interesting example is the so-called script systems, or non-monetary economies. In such models, the node represents agents. The supply units are scripts or coupons. So people request service over time and pay other people service with coupons. A celebrated example is the Capitol Hill babysitting co-op, where people pay their neighbor with coupons for babysitting their children. So the levers of control of interest here are admission control. For example, if there's a trade request coming in, the system can decide whether to decline it or not. When a trade has several possible service providers, the system can also decide who should be the provider. Okay. So here is a preview of today's talk. The goal of today's talk is to introduce to you an online control framework for payoff maximization in the closed queuing network models. Because this talk only has 18 minutes, I will use a simple dynamic entry control to demonstrate the idea of this work. And for general results for more complicated forms of controls, we refer you to the main paper posted online. In this talk, I want to convey 3 key messages. The first key message is that there's a great value in considering the state-dependent control. By state-dependent control, I mean the system controller should be aware of the current supply distribution within the network when making a decision. Many works in the literature, they only consider state-independent controls. So what's the benefit of state-dependent control? Well, first, it enables parameter-free or blind policies. So like policy that doesn't need the system parameters to make decisions. Also, these policies tend to have good theoretical guarantee and great simulation performance. I will show you the simulation result at the end of this talk. The second key message is that for this type of problem, there's an appropriate framework called backpressure. Backpressure control is not something new. It was proposed in the literature, network control literature in the 1990s. This is a family of smartly greedy policies. While they're trying to maximize the payoff, they also take into consideration the distribution of supply by using the queue length as congestion costs. This policy is provably near optimal in many settings. So why can't we just apply backpressure to our setting and solve the problem? Well, it turns out a vanilla version of backpressure suffers from a so-called underflow problem. And this prevents backpressure from being directly applied to many applications, including ours. A key contribution of our work is to provide a systematic fix for this problem. Our fix is using nonlinear function of queue lengths instead of queue length themselves as congestion cost. It turns out this fix has a deep connection with the idea of mirror descent from optimization literature. That's why we call our policy the mirror backpressure policy. In the interest of time, I'll skip the related work. And in the following few slides, I will use a simple illustrative example to walk you through the key elements of our idea. So in this work, we consider a node network represented by the circles here. You may recall in ride-hailing, they are the physical locations. and a fixed number of supply units circulate in the system. We consider a slotted time model, and exactly one demand arrives per period. So the index of time just records number of demands arrived so far. For the tth demand arrival with probability phi jk, this demand has origin j and destination k. We call it of type jk. So this guy wants to go from location 1 to location 3. And the platform needs to make a binary decision, the entry decision. Here, zjk equals to 0 means dropping this demand, and zjk equals to 1 means serving this demand. The entry decision should satisfy a so-called no underflow constraint. This is very straightforward. It just says that to serve this demand, you need to have at least one car at the origin node of this demand. Okay, suppose the platform decides to pick up this customer. Then the platform will collect a payoff of wjk that depends on the type of the demand. And the car will leave the origin node of the demand, relocate it to the destination, and become available again. This is what happens in one time period. And the platform's objective is to maximize the total expected payoff collected over finite horizon t. Okay. Now let's talk about the backpressure policy. So as I mentioned earlier, backpressure policy is very simple. It tries to maximize payoff and use the congestion cost indicated by the queue length to regulate the decision. In our example, the form of backpressure policy is extremely simple. It's a two-line policy. So recall the entry decision is binary. Under backpressure policy, the system will accept a type JK demand if and only if the following score is non-negative and the origin location is non-empty of supply units. So let's take a closer look at the score. The score has three components. First is the payoff of accepting this demand. Second is the congestion cost indicated by the queue length at the origin of this demand, which is Qj, minus Qk, which is the congestion cost at the destination location of the demand. This policy is actually very intuitive. So the more lucrative serving this customer is, the more likely the platform is going to accept this demand. And also, when the origin node has a lot of supply units waiting, the platform is more likely to serve the demand. If the destination location only has a very short queue, the platform is also leaning towards serving the demand because they could relocate a supply unit to the destination queue. So it turns out this very simple policy is provably near optimal in many settings, although not in ours. So why does it almost work? Well, this has a connection to the underlying static problem of the dynamic resource allocation problem we are considering. Let's look at this linear program here. Think of ZJK as the long-run average probability of accepting a type JK demand. So the origin here is just the rate of generating payoff under this policy in the long run. Because in the long run, the rate at which supply units enter a location should equal to the rate it exits a location, right? This is called the flow balance constraint, and it should be satisfied by all the nodes in the network. So this is exactly the constraint here. For each node, there's a flow balance constraint. Also, these TJKs are probabilities, so they should take value between 0 and 1. So this linear program provides an upper bound of the rate you generate payoff in a single period on average. The interesting thing is, under backpressure, the normalized queue lengths actually they function as the Lagrangian multipliers or dual prices of these flow balance constraints, one for each node. The magic thing is, if you update your queue lengths according to the backpressure policy, then the queue lengths will be executing a dual stochastic gradient descent on this underlying static problem. So as you may imagine, if you can show that the queue lengths converge to the optimal dual price, then your policy should be near optimal. Sadly, there's another constraint that prevents this from happening in our setting, which is the no underflow constraints. Recall that no underflow constraints require that we have at least one car at the origin node if you decide to serve the demand. But the vanilla backpressure policy does not naturally satisfy these constraints. Actually, we construct in the paper several examples where vanilla backpressure run into problems where some of the queue lengths are empty. So this is because the vanilla backpressure does not adapt to the problem geometry arising from these no underflow constraints. There were several workarounds proposed in the literature, but they all require strong assumptions on the network, which are not satisfied in our setting. So our research question is there a systematic way to satisfy the no underflow constraints while retaining the advantage of the simple backpressure policy? Well, luckily, we propose this backpressure policy to the rescue. So now let's take a closer look at the vanilla version of backpressure policy. It executes gradient descent on the dual problem. If you are familiar with ordinary gradient descent, it actually assumes an underlying Euclidean geometry. However, in queuing systems, the state space of queue length or dual variables actually works better with non-Euclidean geometry. This is because the queue length has constraints. For example, in open queuing networks, because the queue length cannot be negative, the state space is non-negative orthont. In closed queuing networks, because the sum of queue lengths is fixed, the state space is the probability simplex. There can be more complicated forms of geometry. For example, in bike sharing, each location only has a finite number of docks. So there's a finite buffer size constraint as well. So naturally, we want to find a policy that executes a non-Euclidean version of gradient descent. What's the non-Euclidean version of gradient descent? That's mirror descent, which has been studied intensively in the optimization literature. So simply put, mirror descent is a family of optimization algorithms with one degree of freedom, which is the choice of a distance generating function. So this generating function should be chosen according to the underlying geometry of the problem. In our setting, we'll use the gradient of this function as the dual prices or Lagrange multiplier. We call this function the congestion function. In fact, if you choose the distance generating function to be a quadratic function, then it exactly recovers the vanilla version of backpressure policy. Another great news is that the mirror descent already has an established convergence theory. So this will help trying to prove the near optimality of mirror backpressure policies. Now let's go back to our example. So what's the underlying problem geometry? Well, there are non-negativity constraints for the queues. In the main result, we show that for a family of choice of congestion functions that satisfy a technical growth condition, our main result holds. So roughly speaking, these congestion functions should look more or less as the one indicating in this graph. So intuitively, when the queue length is small, the system wants to provide allocation from being drained of supply units. As a result, the congestion function should decrease steeply as the queue length decreases. On the other hand, when the queue length is large, then we are already safe, so the congestion function can be flat here. Examples of such functions include logarithmic functions, inverse square root functions, etc. And the mirror backpressure policy looks very similar to the vanilla backpressure policy. Again, the entry decision depends on the score, and the score also has three elements, which is the payoff of accepting a demand, plus the congestion cost, now indicated by this nonlinear function here, minus the congestion cost at the destination node, also indicated by this nonlinear function. Here is our main result. We show that under a mild connectivity assumption on the mean arrival rate phi and a proper choice of the congestion function, the suboptimality of mirror backpressure comparing to the best dynamic policy is of this order, k over t plus 1 over k. Let me remind you what these letters mean. So k here is the system size, which is the total number of supply units within the system. And t is the number of demands arrived so far. To make the result more explicit, let's consider a large market regime, where everything speeds up as the system size grows larger. So if you denote the physical time by t real, then a number of demands arrived so far should be k times t real. And we can rewrite the result as 1 over the physical time elapsed so far plus 1 over k. So now you can see clearly as time goes by and as the system size grows larger and larger, the suboptimality gap diminished to 0. The first term 1 over t here is the transient regret, and 1 over k here is the steady state regret. In our paper, we show that this result still holds under regularity conditions if we allow this platform to consider more complicated forms of controls that involve dynamic pricing or assignment control. Now, at the end of this talk, let me show you some simulation results. So in our model, we make a simplifying assumption, which is that the relocation of a supply unit is instantaneous. While this assumption is satisfied in some applications, such as script systems, it's not true in ride sharing, because relocation does take time. So in the simulation, we incorporate this travel time, which is captured by Google Maps. Because of now there's travel time, there's an additional caveat, which is that the number of cars in transit should not exceed the total number of cars in the system. By Little's law, we can write down this constraint as this. On the left-hand side is the average number of cars in transit. So now let's just augment the original static problem with this additional constraint. Take the dual and we arrive at the following policy. We call this the delay-aware mirror backpressure policy. So now, the decision of the platform decides on a more complicated form of score, which involves the payoff of serving the demand, plus the congestion cost at the origin, minus the congestion cost at the destination, and there's also another term that takes into account the travel time of going from J to K. So this actually shows the flexibility of our mirror backpressure framework. But I want to make it clear that this policy is just a heuristic for now, and we don't have a formal theorem for its performance. So here is a graph indicating the performance of several policies. We compared the mirror backpressure policy, vanilla backpressure policy, against the other two benchmark policies. So for the static policy, we mean a policy that knows exactly all the demand arrival rates, solve the underlying static problem, and realize the solution using randomization. This is a prevalent approach in the existing literature. Another benchmark policy is the greedy policy, which simply accepts all the demand requests. Here in this graph, the x-axis is the time of the day, from 8 a.m. to 12 p.m. And the y-axis is the payoff collected, normalized by the optimal value of the static problem. We can see that the mirror backpressure performs the best. It collects around 90% of the optimal payoff. Vanilla backpressure collects around 80%. The static policy collects around 70%, and the greedy policy collects around 50%. The issue with static policy is that it is state independent, so it doesn't perform very well in transients. For the greedy policy, because it doesn't take into account the flow balance in the system, so it has a very poor performance. We vary the number of supply units in the system and do the simulation again, and observe very similar performances. In the interest of time, I'll skip this remark, and it's time to wrap up. To sum up, in this work, we propose an online control framework for the payoff maximization problem in closed-Qian networks. We propose a simple family of policies called mirror backpressure that has great both transient and steady-state performance guarantee. This framework is very flexible. It can incorporate the primal constraint, such as the Little's law constraint in the simulation. It can also incorporate dual constraint, such as the constraints on the queue lengths. It can also be used to incorporate the known information, which I didn't have time to cover today. There are also several future directions of interest. For example, we can use mirror backpressure to incorporate the empty car relocation decisions. And also, because our policy doesn't require the demand arrival rates, it can work in a time-varying environment, which is closer to the real world. Also, we can consider a standard mirror backpressure policy, which takes into account the known information. That's pretty much it. Thank you.